Hello guys, how are you today? So today I'll be explaining the physics AMS of term 2 week 11. Now, let's start with the first question. Drag and drop the correct terms from the box below. Sound can be defined as a what wave motion, and since it is this, it needs a what to travel through. What you need to know is that we have two types of wave motion. We have longitudinal and we have transverse. Now, what is the difference between these two? What you need to know is that the direction of longitudinal is parallel to the direction of wave propagation, and it has compressions and rarefactions. Compression means you are squeezing them together, you're bringing the particles close together, and rarefactions means you are bringing them farther apart. And also, the particles travel with the medium. So longitudinal is parallel, it has compressions and rarefactions, and it travels, so particles travel with medium. Alright, whereas for transverse, what we need to know about the transverse is that the direction of motion is perpendicular to the direction of wave propagation. That means it has what? It has crests and troughs. Alright, so it has peaks and I don't know what to call it. It will look like this. It looks like a sine function. And this also means that particles travel along the medium. Alright? And what you also need to know is that longitudinal waves, they need a medium to travel through, whereas transverse waves, they can travel through vacuum. So again, longitudinal, they move parallel to the direction of wave propagation. They have compressions and rarefactions. They are particles that travel with the medium, and they need a medium to propagate, to move. Whereas transverse, they move perpendicular to the direction of wave propagation. They have crests and troughs. The particles move along the medium, and they can even travel through vacuum. So sound waves, you need to memorize that it is a longitudinal wave motion. And because it is a longitudinal wave motion, okay, I also forgot to mention is that usually longitudinal wave motion could be mechanical. But this is not always the case, only in the case, not only, but in the case of sound, it is both longitudinal and mechanical. Okay, so basically a mechanical waves mean it is a wave that can travel through material or through matter. So definitely we have the mechanical wave to be sound because it can travel through matter. And another type of wave is an electromagnetic wave, which is a wave that can travel through vacuum. So sound waves, they are a longitudinal wave motion, and because they are longitudinal, that means they are mechanical, and because they are mechanical, they need a medium to travel through. So this is all you need to know. However, if they brought for you light, you should know that light is a transverse wave motion, and it is an electromagnetic wave, so it does not need a medium, or it could travel through vacuum. We move on to question number 2. We just explained what a sound wave is. So a sound wave in air, pay attention, they could bring in vacuum. In vacuum, sound wave does not move. But a sound wave in air, it is a mechanical wave, and it is also a longitudinal wave. We move on to question number 3. A water wave can be generated by continuously tapping on water surface as shown below. Drag and drop the correct terms from the box below. What you need to know is that waves, they are vibrations. I don't know if your teacher did about the slinky, which is the spring, okay? But like a spring, it is just a big amount of vibration. So waves are vibrations that transfer what? They transfer energy, okay, without moving a matter. So a wave could pass through, for example, your phone, and it could not cause the phone to move. For example, when your phone is ringing, okay, of course, when it's not on a desk, when you hold your phone up, for example, your phone starts to ring, so it will create a sound energy that has a vibration. So it is a vibration that will not move your phone. It will not move your phone. It will just make a sound and you will be able to feel the vibration passing through your hand. So matter will not move, but energy is being transferred through vibrations. We move on to question number 4. So, where particles of the medium are spread out, here we're talking about a sound wave. You should know in a longitudinal wave, we have two types of I don't know what to call them, two types of cases. We have compression, in which you compress them, you bring them close together, and rarefaction or rarefaction, in where you spread them out. So for rho A, it's gonna be rarefaction, because it is spreading out the medium. Whereas for rho B, it's gonna be compression, because you are bringing the medium close together, the particles of the medium close together. So this is gonna be compression. I'm not sure if I wrote it correct, so let us see in the end. The diagram below shows the variation of the pressure of a sound wave in air at one instant with respect to distance. What you need to know is that this is not the graph of a longitudinal wave. Okay, this is only the pressure distance graph of a sound wave. This is not for the longitudinal wave. Please keep this in mind. So which point represents the description in rho A? The description in rho A, we said it is a rarefaction, in where the medium is spread out. So if the medium is spread out, it is gonna have the least possible pressure. So you're gonna go take it from the least possible value, which is Z. Whereas when it is being compressed, it's gonna have the highest possible pressure. So you're gonna take it from the highest possible value, which is X. Okay, so now we move on to question number 5. What you need to know in question number 5 is that frequency is how many waves or cycles occur per second. Speed is distance over time. The wavelength is the length of a wave from peak to peak, or trough to trough, or rest to rest. And the amplitude, it is the rest position, like the distance from the rest position to the crest or trough. Or in another term, it's the displacement of a particle, the maximum a particle could move. So amplitude, as we said before, it is the maximum displacement of a particle, or the maximum a particle could move. Speed is distance over time. Frequency is how many waves per second. Okay, so the number of cycles or waves completed per second, and the wavelength is very simply the length of a wave. Now, what you need to know about some of them is that the wave amplitude, okay, or the amplitude of a wave, it is proportional to the loudness. So an increase in amplitude increases loudness, whereas frequency is proportional to pitch. So an increase in pitch is gonna increase the frequency, or the other way around. Now, also one more thing before we go, you should know that the sound intensity is directly related to the amplitude squared. Okay, so keep this in mind. We'll move on to question number 6. Consider the 4 diagrams below plotted using the same scale. They need which graph is the loudest. What you need to know about the loudest and not the loudest is that the amplitude, as we said before, it is responsible for the loudness. So the higher the amplitude, meaning the greater the distance from the resting point to the peak, or the other of the down of the peak, I don't know what to call it, this is the amplitude. So in this case, it is gonna be B. However, having more frequency, that means per second, let's say this is 1 second. Per second, if you have more waves, that means you have a higher frequency, but which means you have a higher pitch. So for the pitch, it is graph D. Is that it? Yeah, that is it. We'll move on to question number 7. So a wave in which the displacement of particles is along, keep in mind, along means parallel, the same direction. Now look. Here, this could get you into a small trick. We know that what? We know that the transverse waves, the particles, they will travel along the transverse waves, whereas in the longitudinal waves, the particles travel with the waves. However, with the direction, it's opposite. So the longitudinal waves, the particles are going to travel along the same direction, that means parallel to the waves. So please read it in context. Whereas if they said perpendicular to, or not along the same direction, then it's gonna be a transverse wave. So please read it into context or else you might get a mistake. So along the same direction, meaning parallel, then it is gonna be a longitudinal wave. Okay, we move on to question number 8. They need us to calculate the wavelength of a wave. We are given the wavelength and the frequency. They need us to calculate the speed. What you need to know, the equation is that speed is equal to the wavelength denoted by lambda times the frequency denoted by f. So the wavelength denoted by lambda and frequency denoted by f, they need it in meter per second. So definitely hertz, you're not gonna change it, you will keep it the same, so 12,000 hertz. Okay, but the centimeter you can change it into meters, so times 10 to the power of minus 2. So 25 times 10 to the power of minus 2 times 1200 hertz. So let us see what we're gonna get. We are gonna get 300 meters per second. So very simply, the speed of this wave is 300 meters per second. We move on to question number 9. Here very simply, you should know which statements best describe a transverse wave. A transverse wave, it is either a light particle, or like a light wave, sorry, not a light particle, it's a light wave, not a sound wave for sure. The particles, they move in a direction normal to the wave direction. This is true because normal means perpendicular, so this is correct. Energy is transported with the wave along the medium. This is true. Pay attention. Before they said along the direction of the wave, here they're saying along the medium. When you see along the medium, it is for a transverse wave. They do not move in the same direction as the wave, and they cannot travel with the wave. So very simply, these are the two only options. We move on to question number 10. In question number 10, they said they need what? They need a periodic wave. What you need to know is that a periodic means constant, something constant. So again, a periodic wave means it is constant. So when you're looking at the graph, you have to choose a constant graph. Definitely not this. And we know a wave does not look like this or like this. So its graph is gonna be like this, which is a sine function. So when you see that the graph of a wave is a sine function, you should immediately know that this is a transverse wave. We will move on to question number 11. Which of the following intervals represent the period of this wave? To calculate the period, it could be either from crest to crest, so from top to top. I don't know why I wasn't able to speak. Or from trough to trough, from bottom to bottom. Or from 0 to 0. So you're not gonna take this 0. So my miss taught it like this. She was like, take this one, skip this one, take it. So you take, skip, take, skip, take, skip, like this. So it could be either C, whatever this is, we don't know what it is, so we cannot take it, or AE, or it could be OD. So the period could be OD, or it could be AE. That's it. We'll move on to question number 12. The number of waves that pass a fixed point in medium per second. You should know that frequency is how many waves per second, or how many waves pass per second. This is very simply frequency. It's just stating the number of waves that pass a fixed point per second. So it is frequency. We move on to question number 13. Here you have to memorize that a wave is a train of pulses. A pulse is a disturbance traveling through a medium, and rarefaction is the point along wave corresponding to the maximum displacement. Maximum displacement means the greatest movement, or like the greatest separation of particles. So the greatest separation of particles in the longitudinal wave. We move on to question number 14. So here, as you can see, the direction of the wave is going like this. So it is parallel to the particles that are moving. So because it is going parallel, that means it is a longitudinal wave. Now, this is during what? An earthquake. So what you need to know is that an earthquake is a mechanical wave. Why? Because it needs a medium to propagate through. So always remember majority of the time it is a longitudinal mechanical wave. So here it is a longitudinal mechanical wave. Now they said underline the points at which compressions are observed and circle the points at which rarefaction is observed. So compression, as we said, the particles are being brought close to each other. So as you can see over here, we have 1 and 3 where the particles are really close to each other. So you are gonna underline 1 and 3. Now for the rarefaction, they have to be farther apart, and as you can see, 2 and 4, the particles are going farther from each other because from 5 it's being constant. So definitely 2 and 4 are undergoing rarefaction. We move on to question number 15. These are things you should know. We should know that the sound, it does not move in vacuum. And what you need to know is that if there is a medium where the particles are closer to each other, then the sound can travel faster. So the speed of sound is gonna increase if the medium, its particles are closer together. So definitely it's gonna have a greater speed of sound. Air is gonna have a smaller speed of sound than water. Why? Because water, its particles are closer together. For light, it's the opposite. So for light, the more farther apart the particles are, the faster its speed is gonna be. So it's gonna move like this. Now, comparison between comparison between sound and light, definitely light has a greater speed, no matter the case. And then finally, speed of infrared radiation in the air versus speed of visible light in air. Now, here they are equal because, as you remember before, we took that if they are traveling in vacuum, okay, not in vacuum or air or whatever, or whatever particle in air, vacuum, solid, liquid, gas, okay, because they are made of the same thing. So infrared radiation is light and visible light is light. Because they are made of the same thing, they will travel at the same speed. Okay, so same particle, same medium will travel at the same speed. Now, for question number 16. Satellite laser ranging service uses short pulse lasers, powerful light sources, and sensitive timing devices to measure the distance to satellites orbiting the Earth. The laser pulse is emitted from Earth, reflects from the satellite, and is detected by a sensitive sensor on the ground. The laser signal returns to Earth. Okay, we are given what? We are given the time. We found what? The time, which is 1 times 10 to the power of -2 seconds. Now, the wave of the electromagnetic radiation is this much nanometer, so it's 1064 times 10 to the power of -9 meters. Keep this in mind. And the speed of light is c 3 times 10 to the power of 8. So, very simply, what we need to know is happening is like this. The wave is going like this, and then it's coming back. Alright, so the wave is going 2 times. It will go 1 time up to the satellite, and it will come 1 time back down. So we will find first of all the total distance, and to find the total distance, very simply, it is the speed of light times the time, which is 1 times 10 to the power of -2. So in this case, the speed of light is always going to be 3 times 10 to the power of 8. Okay, but you're going to multiply it by the time, which is 1 times 10 to the power of -2. And you are going to get almost 3 million meters per second. But, sorry, not 3 million meters per second, 3 million meters. But we need to know that half of this is going up and half of it is coming down again. So we're going to divide it by 2 to get the distance for one way, or the one-way distance. So it's going to be 3 million divided by 2. You get 1,500,000. So now you have the new distance in meters. And to change it to kilometers, you are going to divide it by 1,000, or 10 to the power of 3. And you are going to get it to be 1,500 kilometers, very simply. So 1,500 kilometers. Now, what is the primary reason for using electromagnetic waves instead of sound waves? Very simply, is that electromagnetic waves can travel through empty space. This is all you need to know. We move on to question number 17. The diagram below shows the displacement time graph for a longitudinal wave in a slinky. The period, we said the period is what? The period is from crest to crest or the trough to trough. So let us find the period. Very simply, it's gonna be from here all the way to here. So here, this one, it is approximately 0.5. And this over here, it is approximately 0.1. So the period is gonna be 0.5 minus 0.1, which is 0.4. Just like that, we found the period of the wave. Now, the frequency of the wave, to find the frequency, it is how many waves are happening in 1 second, or what we could do is, I know this isn't gonna be really accurate, but so we could draw from this point, we can draw the midline, okay, or the cutting of this wave. All right, and now at 1 second, we are gonna go and we are gonna see at which point does it meet the cutting of the wave, or the let us call this the x-axis. So first thing what I did was I drew the x-axis. After that, I located 1 second, and I was like, okay, it stops at here. So in 1 second, this is how many waves travel. So can you count them? This is 1 wave, so it will finish the wave here. Then this is another wave, 2 waves, and then this over here is half a wave, so 0.5. So this is 1, 2, 2.5 waves. I will explain again how I did it. So I will draw the x-axis starting from where they meet. Then I will take 1 and I will put it over here. And then as you can see, you have 1 wave, it will stop here. Then it will repeat itself again here. And then it will stop, and then it will repeat itself, but it will repeat only half. So it is 1 plus 1 plus half. So it is 2.5. So the frequency, it is 2.5 hertz. Now the amplitude of the wave, very simply to find the amplitude, it is the height or the highest point. So as you can see, each point is 0.1. So this is 1, this is gonna be 1.1. So over here, this is gonna be 1.2. So the highest point or the amplitude of the graph, it is 1.2 centimeters. We move on to question number 18. Here they said, what kind of wave is propagating in the rope? So very simply, as I stated before, okay, the transverse wave, it's always a sine function. It always looks like this. Whereas a longitudinal wave, it would look something like this. It would look like line, space, line, space, line, space, whatever, like this. It will look something like this. This is what a longitudinal wave looks like. So, all you need to know, all you need to memorize is that the transverse waves look like this, like a sine function, okay? Whereas the longitudinal have compressions and rarefactions and whatever. So this is definitely a transverse. Now we need to know, is this electromagnetic or is this mechanical? So very simply, if you go up and read, you will see that the displacement in the diagram, below, shows the displacement of the rope, okay, as the wave propagates through it. So the wave is propagating through the rope. And if it's propagating through the rope, that means it needs a medium to propagate. So because it is traveling through the rope, then it is definitely a transverse mechanical wave. So choose the correct answers to complete the sentences below. The wavelength of the wave. They need us to find the wavelength of the wave. Very simply, to find the wavelength of a wave, you are going to take it from crest to crest. So from here until here. Or if you want it to be more accurate, I would say, first let me just make it a bit bigger. There we go. To make it more accurate, because it seems if you take it from the crest to crest, it's not going to be accurate. You're going to draw the x-axis, okay? And then you are going to take it from the rest point. So rest point, you take it, you don't take it, you skip it, and then you take this rest point over here. As you can see, this is approximately almost if here is 0.7, so over here this is gonna be almost 0.65. okay, let's see what they gave us as options. They gave 0.63, so we're gonna take it because it's the closest to 0.65. The amplitude of the wave, however, the amplitude being the height, it is 20 centimeters but they need it in meters, not centimeters. So to change it from centimeters to meters, you are going to divide by 100. So 20 divided by 100, you are going to get 0.2 meters. For question number 19, match each term to its corresponding definition. The rate at which the wave carries the energy through the unit area at a right angle to the direction of travel. This, all you need to know is that it is the sound intensity. Okay, now the property of sound determined by the amplitude. The wave amplitude determines the loudness, and then finally frequency will determine the pitch. We'll move on to question number 20. This again is just like more definition. We said that frequency is proportional to the pitch, so an increase in frequency increases the pitch. Okay, which property changes the amplitude of a sound, or changes when the amplitude of a sound is increased? Very simply, we know that amplitude is directly proportional to the loudness, so the amplitude will increase the loudness. Now finally, the amplitude, what you need to know, the relation between amplitude and intensity of sound, or sound intensity, is that sound intensity, I, we're going to label it I, is directly proportional to the amplitude squared. So the amplitude of the sound wave is doubled, meaning I is directly proportional to 2a squared. So I is directly proportional to 4a squared, because you're going to square the 2. So now what happens to the I? It will be multiplied by 4. So very simply, you double the amplitude, then you are going to quadruple the intensity of the sound. So let's submit, and hopefully there are no mistakes. So thank God we don't have any mistakes. Sorry for the cutoff, because my parents came into the room. So anyways, thank you guys for watching. I hope you enjoyed, and have a wonderful day.